Right. This is section 8, which is where we actually are going to apply Gauss's law and use that to calculate electric fields. Okay, it's different for a bunch of different cases. We're going to look at the point charge, and there's a spherical conductor. I think there's a line of charge. There's a spherical insulator, line of charge, concentric cylinders, and a plane of charge and parallel plates. Yeah, it's a mess. There's a lot. Okay, but it's mostly graphic organizers, and the organizers don't take too long to fill in. Okay. The point charge is consider a point charge Q isolated from other charges when you wish to find the electric field at distance R from the charge. Describe an appropriate Gaussian surface to use to find the electric field. Draw it on the diagram. So, because the point charge is basically a sphere, I think the best surface to use here that fits the three tenets from earlier is to just draw a bigger sphere. That's the simple solution. Okay, and the sphere is going to have a radius r. Okay, it's going to be centered, it's going to be concentric with the charge. So I'm going to say it's a sphere centered on charge, okay, with radius r. Okay. Okay. To find an expression for the electric field at distance r from the charge, I actually would have to set up my the my integral, okay? And I'm going to use the organizer on the next page to show you how to do that, okay? What does it mean to be in the bulk of a conductor? What it means to be in the bulk of a conductor is that if you have a a sphere of charge, and this is more for when we get to the conductors. If you have a sphere, if you're like in the metal or inside the conductor, then it would be in the bulk of a conductor. And for the notes packet, you're never gonna say yes, because if you're inside the bulk of a conductor, E field's 0, and that's just too easy, right? So let me get an orange pen here. So I'm gonna say no, I'm not in the bulk of a conductor. Okay. The surface I'm going to use, this is supposed to be a sphere right here. Okay. So I'm going to use this. Okay. Shade in the air the surface that has flux through it. So if we put a big sphere around the charge, then all of the surface area is getting the flux through it. Okay. And then an important geometric parameter for us is, of course, the radius, which is just going to be r. Okay. Now, the integral, okay, the surface, it's just a surface integral, okay? All that means is that this is really going to resolve out to being E times the surface area with flux through it, okay? So you don't actually have to do any integrals here. All you have to do is take E and multiply it by the surface area that has flux through it. Well, that's going to be the whole surface area of the sphere, and the surface area of a sphere is 4 pi r squared. Okay? So that's literally it. You don't actually have to take any integrals here. That's all you have to do for that. Okay? Okay. The surface is enclosing a discrete charge. Discrete charge is where it's like point charge or multiple point charges. Okay? And the enclosed charge is just equal to Q as we're given in the problem. That's all we have to do. Okay. If we had multiple charges enclosed, then we would obviously have to change that. We might have to add stuff up, but that's not not that big of a deal. Okay. Then we can plug that into Gauss's law. Okay. And this is where we then just say, okay, we already evaluated this part right here. This is going to be E dot 4 pi r squared equals enclosed charge is just Q, and then epsilon naught is a constant. All you have to do now is solve for E, and the easiest thing to do is just divide by 4 pi r squared. Okay, so I get E equals Q over 4 pi epsilon naught r squared, which by the way, 1 over 4 pi epsilon naught, that's just K. K Q over r squared. So we literally just derived using Gauss's law that you can find the electric field at any distance using kq over r squared. Okay. So solved that. We did good on that one. We saw that it ended up being E equals kq over r squared. Okay. Okay, for a spherical conductor, this is where we have a a solid sphere, and it's a conducting sphere, so it has charge on it. Okay. Well, again, this is basically a larger point charge. So what I'm going to do instead is I'm going to make my Gaussian surface. I'm just going to make it a even bigger sphere. Okay. And I'm going to make it have a radius little r, which this is the confusing part. Little r is going to be greater than big R. Okay. So I'm going to say sphere of radius r centered on, or I'm going to say concentric with conductor. Okay. Concentric with the conductor. Okay. Okay, Gauss's law to find an expression for the electric field at distance r from the charge where little r is greater than big R. This is where you're actually going to have to solve it out. This is actually going to end up being the exact same thing. I don't even need to show this. This is going to be the exact same thing as we got earlier, right? Because nothing changes here. This is just a charge that has a large radius, right? So we can simply say that this is going to, the surface integral of E dot dA equals Q enclosed over epsilon naught. All we have to do is we already know this left-hand side is going to evaluate to being E dot 4 pi r squared, okay? And then the right-hand side is just going to be Q, the enclosed charge, over epsilon naught, okay? And once you get all of that, okay, you solve it out and it ends up being the exact same thing. E equals Q over 4 pi epsilon naught times r, little r squared, okay? And that is the same thing as KQ over R squared. Okay, so it ends up being the exact same thing. Okay, I don't have to do the whole thing again because it's identical to the previous example that we did. Okay. What is the electric field a distance little r from the center of the sphere? If little r is less than big R, this is going to be in the bulk of the conductor, so it would be 0. 0 because you're in bulk of conductor. Okay. And what this means is that the charge given to a conductor, it's going to, so all excess charge, okay, is on the surface of a conductor. Okay. So all that excess charge moves to the surface of the conductor. There's none inside of the conductor. It all goes to the surface. Now, if it's an insulator, then it can be found. It can be found in the bulk of it. So it's important to read the problem completely because, for example, this is a spherical insulator, which means that it can have electric field in its bulk. Okay. If you're in the bulk of an insulator, you can have electric field or electric you can have charge in the middle of it, and you can have E field inside of the bulk of it. Okay. If you go outside of the sphere, it's the same as the point charge in the spherical conductor. The reason is because you have the same enclosed charge Q. Okay, and you're going to use the same surface. Okay, which is a sphere. Okay, it ends up being the exact same thing. Okay, if you want to see that proven, you could ask, but I'm not going to. It's the exact same thing. It ends up being the exact same thing. Okay. How much charge is enclosed in the sphere? You would have to. The way that you can do this, you can solve this, is actually going to be using a very familiar method. Hopefully, it's at least somewhat familiar to you. If it's uniformly distributed over the volume of the sphere, if the charge is uniformly distributed over the volume of the sphere, then that means that the charge is all throughout the sphere. Okay, that means even down to the core. Okay, so all throughout the volume of the sphere, not just on the surface, but all throughout the volume of the sphere. Okay, but if it's uniform, then I can set up a ratio, which is that if I were to take out like a little chunk of the sphere, okay, maybe like a little piece of it, just a little part in the center of it, then I can figure out, I can relate the portion of charge that I've taken out to the total charge by setting up a ratio by also comparing the volume that I've taken out to the total volume of the sphere. So I can do Q enclosed over the amount of volume that I've taken out. Okay, and this is radius little r. Okay, little r cubed. And I can set that equal to the ratio of the, because if it's uniform, these ratios should be equivalent, the total charge over the total volume of the sphere. Okay. Now this might look familiar to you if you remember back in last unit. Okay. And if you solve this out, if you actually try and get Q enclosed by itself, because that's what we're trying to solve for, Q enclosed by itself, you'll actually see that quite a bit of stuff is going to cancel out here. Your 4/3 pi are going to cancel out on both sides. Okay. And you'll end up with Q enclosed equals little r cubed over big R cubed times Q total. Okay. This is identical to an example that we did in Unit 7. This is identical to a mechanics example that we did. That was the Hull to China problem, or you might know it as the gravity train problem. That's actually the proper name for it, is the gravity train problem. Okay. So this is actually identical to that problem where if you drill a hole through the earth and then you drop something in, you can figure out that's the amount of the oh gosh, it was like the mass enclosed. It was the mass enclosed. Yeah, it was the mass enclosed of in like a certain sphere or whatever, and that actually does have an effect on the gravitational field as well. And you're going to see it actually has an effect on the electric field. Okay. Okay. So now it says to find the electric field inside of the insulator, and we can use the organizer on this previous page to solve that for us. Okay. We are in the bulk, but we are not in the bulk of a conductor. We're in the bulk of an insulator. So I'm going to have to say no to this, even though I am in the bulk, I'm in the bulk of an insulator. Okay. My surface, I'm using a sphere. Okay, we've already established that. And then I'm using, this is my distance, little r. Okay, I'm using this shape right here. Okay. We already know what this is going to end up evaluating to, because it's the exact same as it's been. E dot 4 pi r squared. Okay. And the surface, now instead of it enclosing a discrete charge, it's going to enclose a distributed charge with uniform density. Okay. So this is, instead of doing a discrete charge, we're now doing a distributed charge because it's distributed throughout it has uniform charge density throughout the whole volume of it. Okay. So so instead of using instead of saying geometry, I'm going to say volume. Okay. The enclosed geometry, it would either be area or volume. In this case, it's going to be volume. Okay. So I would do the enclosed charge over the enclosed geometry. So Q enclosed over 4/3 pi r cubed. Yes, I already did this. Okay. Q over 4/3 pi r, capital R cubed. Sorry. Okay. And I already solved this out to figure out what the Q enclosed is. And I got that it was equal to Q times r cubed over capital R cubed. Okay. And that's what we had solved earlier. Okay. And if I continue into Gauss's law, all I have to do is just take the expression I wrote earlier, 4 pi r squared equals the Q enclosed, which is going to be capital Q, r cubed over capital R cubed over epsilon naught. Okay. I can move that capital R down to the bottom, and I'm going to do that here in a second. And I get the E field is equal to Q, it should be QR, okay, because I can cancel out some of the stuff here. I can actually cancel out these R's, okay. So I just get QR 4 pi epsilon naught times capital R cubed. Okay, and this does simplify to KQR over R cubed. Now, if you remember, we did actually calculate in the previous unit. We did gravity. We did like what was the gravity or the force? What was the strength of the gravitational field at that distance or whatever, right? And we ended up getting something kind of similar to this, where when we solved it, we did the whole to China problem, it ended up being something like. Or sorry, the force of gravity. Force of gravity was equal to something like G M M. I think it was like just GM times R over capital R cubed. It was something just like that. I can't remember it off the top of my head, but it was just like that, right? And that was just G. Sorry, not F sub G. That was just G. So uh, this is very identical to this. And this actually brings up something important that we do need to talk about mechanics wise, and that is something called the hollow earth theory. And the hollow earth theory simply states that if the center of mass of the center of mass, I'm actually just going to show you because I wrote it all down on the key, and I don't want to rewrite it all down. So if you want to write this down, you should. This doesn't have anything to do with what's up here. It's just a completely separate aside. But assuming the center of mass doesn't change, a planet of radius r and mass m is gravitationally indistinguishable from a hollow planet of radius r and mass m. So if you have the same mass and the same radius in two planets and the center of mass doesn't change, then the two planets are going to be identical to each other. And then inside the planet, your gravitational field is going to be zero. So planets function almost exactly how conductors do in electrostatics. Okay, but with gravity, of course. Okay. Okay, electric field distance, we already solved that out. It ended up being that it was E equals KQR over R cubed, capital R cubed, right? Okay, so if we draw this on a graph, you're going to notice that as you go from the inside of the conductor, from the very center of the conductor out to its outer edge, your E field is going to gradually increase. Okay, it's going to gradually increase. Okay, because you'll notice that this value of R is increasing, so then the E field should increase as you go. Once you get to the edge of it, it's going to turn into a point charge, and then you get that nice inverse square relationship that we always see. Okay? So you get a linear segment and then inverse square. Okay? Okay. Now, this is a line of charge or maybe like a wire you can think about. Okay? In this case, what I'm going to do is because the wire is basically a cylinder, I'm going to make my Gaussian surface here a cylinder, concentric with the wire. Okay? And I'm just going to make it some, it doesn't really matter the length I make it. I can make it, I'm just going to make it a length L, okay? And then it's going to have some distance R, okay? The radius of the cylinder, okay? Okay. Or let's use little r. Sorry, I'm just going to try and be consistent here. I'm going to use little r. And this goes out to a point P so that we can figure out the electric field of distance at a point P, or I guess a distance r, right? Doesn't matter. So it wants us to fill in the organizer on the next page, so I'll show you how we can do that one. Okay. For a line of charge, again, we're not inside the bulk of a conductor, unfortunately, right? Wouldn't that make things so much easier if we were? Okay. We're not inside the bulk of a conductor. And we're going to pick a horizontal cylinder as our shape, okay? Now, the thing that's important is that the flux is not at all going to cut through the top ends of the cylinder. It's only going to cut through the the little well, I don't know, the whatever of the cylinder, right? It's going to cut through the length of the cylinder. Okay, it doesn't cut through the ends of the cylinder. It only cuts through the length of the cylinder. Okay, the radius is right here. Okay, a little r, and then the length of it is just L. Okay. And when I get this integral, right, this is going to be E times the surface area that the flux flows through. I'm looking for the surface area of just the part that wraps around the cylinder, not the ends. I don't care about the end part, okay? Thankfully, the equation for surface area of a cylinder is broken up into two parts. You get the length of the part you get the surface area of the length, and then you get the surface area of the circles. I don't need the circles, so I can cut that part out. So it just ends up being 2 pi RL. Okay, the surface area of just the cylinder's uh, length. Okay, the surface is going to enclose a distributed charge with uniform density. Okay, and when I do this, okay, I can set my ratio enclosed charge over enclosed length. This is actually going to be enclosed length instead of geometry here. Okay. If I do, this is going to be total charge over the total length equals the enclosed charge over the enclosed length. Okay. Well, charge over length is just lambda. The charge density equals the enclosed charge over the enclosed length. Okay, so if I want to get enclosed charge by itself, all I got to do is multiply Q enclosed is equal to lambda times L. Okay, that's all I have to do. Okay, and L would be, I guess, technically the enclosed L as well. Okay, but since the L that we've enclosed is going to be is we've already defined as just L. I guess I don't really need to stay enclosed right there. Okay. Okay. So then now we're moving along and we're plugging into Gauss's law now, and all we have to do is we just get E dot 2 pi RL equals lambda times L over epsilon naught. And all we got to do now is just divide the 2 pi RL on both sides. You can tell right off the bat that we can cancel out our L's, okay? And so then this would just become E equals lambda over 2 pi r epsilon naught. Okay, and that's the E field for the line of charge. Okay. Okay. The next page talks about concentric cylinders. Okay. You see this phrase right here that says edge effects, this means, or you might see it also referred to as fringe effects. This is when the E field curves and spreads out. Spreads out at edge of conductor. Okay. It's by convention we ignore the edge effects or the fringe effects, and pretty much every time on the AP exam that you see them, you're going to ignore them. Okay, there's not it's almost every I think it's a convention. It says on the formula sheet that by convention they do not use edge effects or they ignore fringing effects on conductors. Okay. Solid cylinder of radius A is concentric with a cylindrical shell of inner radius B and outer radius C. Both materials are conductors. The inner conductor has a net charge Q, and the outer conductor has net charge, little q and then big Q. Both conductors have length L. Ignore the fringing effects. Okay. Determine the electric field at a distance r from the axis in each of the following cases. If r is less than A, okay, if r is less than A, then you are inside the bulk of a conductor and the E field is equal to 0. Okay? If A is less than R is less than B, okay, then you would have to set up your surface integral, okay, and it's going to look just like the wire, okay, dot dA equals Q enclosed over epsilon naught, okay, but instead your Q enclosed is just little q, okay, because you're enclosing, okay, you're enclosing just the little cylinder, okay. And so I already know what this is going to evaluate out to. E dot 2 pi RL equals Q enclosed, which is just little q, epsilon naught. And then I divide both sides by 2 pi RL, and I get the E field is equal to Q over 2 pi epsilon naught L. Okay. If you're right here, B is less than R, which is less than C, or sorry, B is B is less than R, which is less than C. So R is in between B and C. That's going to be right here. And you're also in the bulk of a conductor. You're in the metal of the conductor. So this is 0. Okay? In a conductor. Okay? And then if you're going out past C, that's going to be like enclosing the entire cylinder. Okay? That's going to be, again, surface integral E dot dA equals Q enclosed. This is not going to change all that much. The only thing that's going to change is that your enclosed charge is now big Q plus little q. So this is actually going to look the exact same as this. You do E dot 2 pi RL equals Q plus little q over epsilon naught, and then when you solve it out, you'd end up getting the exact same thing you got earlier, except instead you have Q plus Q on the top. Okay. Okay. Um, and another, oh, and I completely forgot there should be R's in the bottoms of both of these. I don't know why I missed that, but there should be R's in the bottom of both of these. So I should put, I guess I can put R in the front here. I guess I can put R in the front here. Yeah, there should be R's on the bottoms of both of those. Okay. What is the surface charge density on each of the following surfaces, assuming the charge is distributed and no charge resides on the ends of the cylinders? If you're at a distance A, so that's going to be on the outer that's going to be on the outer what am I trying to say? On the surface of the smaller cylinder. Okay. If you're trying to get that, the surface charge density is this is lowercase sigma. Okay, we do use this sometimes for charge density. This is going to be the charge per area. So you would do the charge that you take the charge that you have on it, little q, and you divide it by the surface area that that charge resides on, which is going to be the length of the cylinder. So the total charge is little q, and then we divide it by 2 pi RL, okay, which is the surface area of that cylinder. On B, okay, what's going to happen at B is it actually is going to have opposite sign charges as what's on A, because A is pulling opposite sign charges together, and we'll see that a little bit more here in a second. So I would put sigma equals, it's going to be the same thing, negative Q over 2 pi RL. Okay? Or I guess it would actually be B. Sorry, it would actually be BL, because the distance is no longer just little r, it's going to be out to B. Okay? Or I guess you could use r, because if r is equal to B, I guess it doesn't really matter. You could do either one. And then for r equals C, this is going to be, you're now having to, it's now going to have both of the total charges on it, okay? So Q plus little q. And the reason for that is because of something with the nested conductors, which we'll talk about in like 2 sections, okay? So sigma is equal to big Q plus little q over 2 pi RL, okay? Or CL. You could use C or you could use R. It doesn't really matter. I could have used A right here if I wanted to. Doesn't really matter, okay? The important thing to consider is that and this kind of does connect with the nested conductor stuff that we'll talk about a little bit later. But let's say that, for example, on the surface of the inner cylinder, we had 4 positive charges. Okay. What's going to happen is if you have 4 positive charges here, they're going to pull 4 negative charges to the inner surface of the sphere. And they're going to hold them in place because they're attracted to each other. They're going to hold them there, okay? Well, then what happens is that these positive charges drive the positive charges on the outer cylinder away. So then you would see that you'd get your positive charges rearranged onto the outside. Well, when you connect the outer conductor to ground, these positive charges want to now leave through ground because they are not they do not like the positive charges being in the center. So they leave. If you then connect the ground to the outer conductor, you would move all the positive charges away, okay? And all Q plus Q charge on outside surface, okay, escapes to ground, okay, leaving negative Q on the inside surface, on inside surface, okay? Okay, all Q plus Q charges on the outside surface are going to escape to the ground, and all you're left with is equal magnitude, opposite sign charges from the inner cylinder. Okay. Okay, and then we have the plane of charge and the parallel plates. I guess these are the last two right here. So the plane of charge, okay, is an infinitely large plane of charge. It's got an area charge density of sigma. Draw a Gaussian surface on the diagram and determine the electric field strength at distance d from the plane. Use the organizer on the next page. Okay, so when I draw my surface, the best surface that's going to work for this is going to be a cube. Or I'm not going to call it a cube. Let's call it a rectangular prism, okay, because it doesn't always have the same sides, okay? Okay. Okay, so there's my cube. Okay, I've drawn it over the surface. And what's actually happening is half of the, and let me also give you like a side view here too. Okay, here's like my side view. Okay, half of it is being cut in half basically by the Gaussian surface. Okay. Okay. And what you're going to notice is that I'm going to define it's a distance d from the plane. So I'm going to go from the plane up to here is a distance d. So that means that the total height of the Gaussian surface is going to have to be 2d. Okay. Okay. Now that I've defined my Gaussian surface, I can use the organizer on the next page to solve it. Okay. We are not in the bulk of a conductor. We never have been. We never will be. Okay. At least in the notes packet. In the homework, maybe you get some in there. Okay. I'm going to use I've already said I'm going to use the prism, okay? And what I'm going to use is that the flux is only going to go, I'm going to say the flux only goes through the top and the bottom, okay? So the area, we're going to say it's equal to A. One face has an area of A. And then we've also said that the height here is equal to 2D, okay? So when I do the surface integral, the only area that's getting the flux is these top and bottom faces, and so the total area getting flux is just 2A. Okay. This is a a distributed charge with uniform density. So I'm going to go this path. The enclosed geometry, I'm looking at area, the enclosed area. This is really just going to be, I already know the charge density is sigma equals Q over the area. So I can figure out that Q enclosed is really just going to be sigma times the area that's enclosed, okay? Is really just going to be sigma times the area that's enclosed, okay? Or the total area of the plate, okay? Okay. So then, when I plug this into Gauss's law, okay, I should see that this ends up just being E dot 2A equals enclosed charge, which is sigma A over epsilon naught. And you should notice that your A's can cancel out, and so you're left with a pretty basic looking equation, which is just E equals sigma over 2 epsilon naught, okay? And that's not that. I mean, that's a pretty simple E field equation. I didn't, the derivation is probably, was looked a lot more complicated than it actually is. And it's really not that bad. So E equals sigma over 2 epsilon naught. Okay, that's what I ended up getting for the electric field strength distance from the plane. Okay, if you have two parallel plates, okay, I can prove to you that so they each carry opposite signs. They each have the same area charge density. They're infinitely large. They're parallel to each other, and they have again opposite sign. So you'll notice that the field goes from the positive to the negative plate. What I can do is I can show you that no field exists outside the plates. Okay. Because if I draw my Gaussian surface to encompass both plates, then you'll notice that the Q enclosed is equal to 0 because I have the same amount of positive charge enclosed as I have negative charge, so it ends up being 0. Okay, so if both plates are enclosed, then Q enclosed equals 0, so E field must be 0. Okay. To determine the electric field strength between the plates, it's going to be very. All you have to do is you're going to use the Gaussian surface still, but the only thing you have to do and kind of change about it is that instead of what am I trying to get at? Instead of enclosing only or both plates, you're just going to enclose one of them. Doesn't matter which one you enclose, just as long as you enclose one of them. This is going to be, I'm going to say this is my distance. I guess we can say that's like my distance d, so it has a height 2d again, okay? And when I do the integral, this is going to be a little bit different because only one face of the Gaussian surface is getting flux through it, okay? Q enclosed over epsilon naught. Again, I can rewrite this. The only area that's getting the flux is just 1A. So this is going to be E times A equals Q enclosed. I've already determined is going to be sigma times the area, okay, the area of the enclosed area of the plate over epsilon naught. And then all you have to do is cancel out the A's, and you're going to see that you get E equals sigma over epsilon naught. Okay, that's all you have to do for that. Okay. Okay, that should be it. I'm pretty sure there's not another section. Yeah, there's another section, but I'll do that in another video. So I guess I'll catch you in the next one. Okay.